Welcome to this explainer. We're going to be unpacking a monumental transformation that's happening right at the foundation of AI memory today. We'll be looking at exactly why the bottom layer of high bandwidth memory, what we call the base die, is completely rewriting the rules for the entire semiconductor landscape. It's a massive shift, and I'm super excited to dig into it with you.
Okay, let's jump right in. Take a look at that glowing copper layer sitting right at the bottom of the stack on your screen. For years, memory was really just passive storage, right? Just a place to park your data. But what we're looking at here is the literal logicification of memory. That active base die at the bottom, it's no longer just a structural foundation to stack things on, it's actually a highly complex logic hub that plugs directly into the GPU interconnects. And this little glowing layer is triggering a massive paradigm shift in how AI hardware fundamentally operates.
So here's exactly how we're going to break this all down. First, we'll cover the great shift of the HBM4 paradigm, then dive into the physical limits of 2048-bit expansion. After that, we'll tackle the hotspot thermal management dilemma, look at how memory evolved into a logic processor, and finally wrap up with the global hegemony battle between Samsung and SK.
All right, let's kick things off with Section 1, the great shift of the HBM4 paradigm. We're moving way beyond simple stacking here.
Take a look at this graphic. Right beneath that pristine stack of memory layers, you can see this highly complex glowing circuit board hovering there. We are firmly past the era of just blindly piling memory higher and higher to get more capacity. In this HBM4 generation, the core focus has totally shifted downwards. That bottom chip, the one you see illuminated in blues and oranges there, that's the boss now. It actually dictates the overall system performance and optimization. I really love this skyscraper metaphor on the screen to help visualize it. Look at the top right. Those core dies act as this storage residence. Basically, they're the apartments where the actual data lives. Then, running through it, you've got the vertical transport, those copper pillars, the through silicon vias, or TSVs. Think of those as high-speed elevators shooting your data up and down. But down at the bottom, that base die, that is the control center. It's the foundational logic layer managing absolutely every piece of external traffic, plus keeping the structural integrity for the whole building above it intact.
This slide really highlights a stark architectural contrast. Over on the left side, you've got HBM3 and older generations. They function strictly as a passive data warehouse, essentially just a concrete room passing signals straight through, nothing fancy. But look over on the right. The HBM4 era transforms this entirely into an active logic chip. Because AI demands are just off the charts right now, this foundation suddenly needs advanced 4-nanometer class logic nodes. It's actively executing complex physical and control logic, totally leaving behind its old identity as just a passive bridge.
So what's actually driving this drastic overhaul? Well, it all comes down to physics. That brings us to Section 2, the physical limits of 2048-bit expansion.
To feed these next-gen AI GPUs, we literally have to double the width of the data highway. We're making a massive jump from a 1024-bit interface in HBM3 to a staggering 2048-bit interface in HBM4. Check out those orange arrows on the slide that represents data traveling at insane speeds, up to 13 gigabits per second per pin. That pushes total bandwidth to over 3 terabytes per second per stack. You just can't shove that much data through a passive routing layer anymore. It absolutely demands highly advanced, synchronized logic control right there at the traffic node.
Now here is where things get really tricky. What happens when you activate 2048 lanes all at the exact same time? You run into 3 catastrophic physics problems, as you can see in these 3 graphs. First, on the far left, you get voltage drop. Imagine thousands of lanes instantaneously demanding power. The supply just tanks dangerously low, which risks major system stutters. Then in the middle, we have simultaneous switching noise. Basically, packing thousands of active wires so closely together creates this intense electromagnetic interference that can literally flip bits and corrupt your data. And finally, on the right, clock skew. Across a chip area this wide, even microscopic variations in physical distance means signals arrive at slightly different times. That completely destroys data integrity.
And solving those physics problems by putting advanced logic right under the memory stack, well, that creates a brand new threat. Let's get into Section 3, Hotspot, the thermal management dilemma.
Cramming a high-performance 4-nanometer logic processor directly beneath a super dense stack of memory creates an absolute thermal nightmare. Take a look at the heat map diagram here. See that intense heat radiating in deep red and amber? That is a localized hotspot exceeding 95 degrees Celsius. And worse, that immense heat radiates straight upward into those blue layers, which happen to be highly temperature-sensitive DRAM cells. Not a great combo. Let's break down exactly why this upward heat transfer is so devastating. Step 1, the logic density down in the base die generates extreme localized heat. Step 2, physics takes over, and that heat naturally transfers straight upward into the DRAM. Step 3 is where it gets bad. Those elevated temperatures cause the microscopic capacitors inside the memory cells to rapidly leak their stored electrical charge. Which leads us to Step 4. To stop catastrophic data loss, the system is forced to perform constant, incredibly power-intensive refreshes. So ironically, this massive thermal burden ends up dragging down the very system performance you were trying to improve in the first place.
So, how did the engineers fix this? They got brilliant. Section 4. Memory evolved into logic processor.
If we deconstruct the base die blueprint here on screen, it reveals a really strict architectural division. Look at that pink outer rim. That's the PHY, or the analog physical layer. Its one and only job is converting raw bits into physical electrical signals across the bumps. But then, look at the center. That is the digital logic controller. That's the brain. It's in there deciding read and write timings, managing addresses, and basically orchestrating the incredibly complex dance needed to keep this whole system stable.
Let's look a little closer at how this new digital brain operates, relying on the three main pillars you see on the slide. First up, signal timing coordination. It's precisely aligning thousands of distinct signals so they actually arrive at the GPU without tangling up into a huge mess. Second is intelligent power management. It actively suppresses those severe voltage drops we talked about in real time. And the third pillar, real-time self-test and recovery. It autonomously hunts down faulty microconnections among the 2048 pathways and actually reroutes data through viable backups on the fly to guarantee yield. It's basically a self-healing foundation, which is wild.
Integrating all this creates what we call a massive controller offload effect. Historically, the big GPU processor layer sitting at the top had to handle tedious stuff like address translation, data reordering, and compression. But now, just follow those downward-pointing arrows on the graphic. Those functions are physically absorbed by the base die layer at the bottom. By sorting and compressing data directly underneath the DRAM, the system drastically cuts down on unnecessary data movement going back up to the GPU. That dramatically reduces latency and saves a huge amount of system power.
Okay, but how do you actually build a marvel like this? That brings us to our final chapter, Section 5, Global Hegemony, Samsung versus SK. Because the physics constraints of HBM4 are so incredibly extreme, these two memory giants have chosen entirely different survival philosophies. It's created this high-level binary split in the industry. As you can see on the left, Samsung is betting everything on an all-in-one vertical integration strategy, basically keeping the whole shebang in-house. Meanwhile, on the right, SK Hynix is relying on broad ecosystem partnerships, aligning themselves very closely with manufacturing giant TSMC and GPU king NVIDIA.
Let's start with Samsung. Their key advantage here is the sheer speed of internal feedback. Follow the circular arrows in this diagram. Because Samsung actually owns the DRAM factories, the 4nm foundry, and the advanced packaging facilities, they have a superpower. If they discover a power anomaly down in the base die's physical layer, say a critical warning, they don't have to call up an external partner to fix it. They can immediately and structurally redesign the thermal structures in the DRAM or alter the TSV routing internally. This hyper-fast, single-factory ecosystem drastically reduces their iteration time.
On the flip side, SK Hynix is heavily leveraging the power of external validation. By choosing to fabricate their base die over a TSMC, they plug directly into a shared design environment. Now remember, TSMC makes the dominant AI GPUs for NVIDIA. Therefore, when SK Hynix designs their memory base die using TSMC's exact voltage standards and physical layouts, they virtually eliminate any compatibility risks. It ensures this completely seamless integration straight into the existing AI hardware supply chain.
Ultimately, regardless of whichever strategy ends up winning out, the final result of this base die evolution is just staggering. We are unlocking the HBM4E leap. We're looking at a future of custom HBM literally acting as a coprocessor, pushing pin speeds to 16 gigabits per second and hitting a massive frontier of 4 terabytes per second bandwidth per single stack. The base die really is the master key that unlocks next-generation AI efficiency.
The physics are completely unforgiving, the thermal hotspots are intense, and the absolute need for flawless logic integration is non-negotiable. So what do you think? Will Samsung's absolute internal control win the day, or will SK Hynix's external ecosystem validation prove to be the more reliable path? Who is going to conquer the trillion-dollar HBM4 yield battleground? The answer is being engineered beneath the memory right at this very second. Thanks for hanging out with me on this explainer, and I'll catch you next time.